Welcome to Bodhi Unified Flow. I am Dr. Marimuthu, your host. Here, we simplify complexity and amplify performance. Today, we're jumping straight into one of the most critical stages of any engineering project, the best practices for the design phase, specifically during planning and pre-construction for structural design. We've got a comprehensive explainer ahead of us covering international codes, geotechnical reports, seismic analysis, and a whole lot more, so let's get right into it. Our agenda today covers 6 core technical pillars. 1. Global codes and standards. 2. Geotechnical investigation factual reports. 3. Advanced seismic dynamic analysis. 4. Independent third-party design checks. 5. Robustness and progressive collapse. And 6. Lifecycle durability and waterproofing.
Here's exactly what you're going to take away from this explainer. A rigorous, multi-codal understanding of how to plan, analyze, and safeguard structures right from the very start. We're synthesizing global best practices, so you walk away with a truly holistic perspective on structural resilience. Okay, let's kick things off with Section 1, Global Codes and Standards. It's actually fascinating how much philosophical divergence there is and how we calculate safety across the globe. Take European and Indian codes like Eurocode 3 and IS 800. They use a partial safety factor approach, applying separate, granular safety factors directly to material properties and loads. But then you look at American standards like AISC 360 or ACI 318, and they rely on load and resistance factor design, using a single calibrated resistance factor. This isn't just theory. It drastically changes your material volume. The exact same column under IS versus AISC can require completely different tonnages for the exact same loading conditions. And this divergence is exactly why practicing globally keeps us on our toes. For instance, IS 800 and Eurocode rank sections from Class 1 down to Class 4. If you want high seismic ductility, you absolutely need a Class 1 section. But the American code, AISC 360, it lumps sections into compact, non-compact, or slender. That compact category actually merges what Indian and European codes strictly separate as Class 1 and Class 2. So if you just directly translate a compact section into an international project without checking those specific width-to-thickness ratios, you are drastically altering your expected seismic ductility. It's a huge deal. Moving on to Section 2, Geotechnical Investigation Factual Reports. Modern harmonized standards like Eurocode 7 have totally revolutionized how we handle soil data by forcing a strict 3-step sequence. This completely eliminates those dangerous interpretive overlaps. Step 1 is the factual report, just pure, raw field data, zero opinions. Step 2 is the ground investigation report, where the designer actually interprets that data to give us derived parameters. And Step 3 is the Geotechnical Design Report, which shows exactly how those interpreted parameters are applied to design a safe foundation. The really crucial shift here is that geotechnics has finally fully embraced limit state design. We're moving away from that massive, old-school global factor of safety and adopting a reliability-based framework that handles both ultimate and serviceability limit states. By treating partial factors statistically, like defining characteristic soil strength as the 5% statistical fractile, we massively reduce the probability of the actual soil strength falling below our design strength. It perfectly aligns your foundation's reliability with the superstructure. All right, let's shake things up with Section 3, Advanced Seismic Dynamic Analysis. As standard static methods become pretty much obsolete for complex structures, we have to ask ourselves a critical question during the pre-construction phase. What are the specific triggers that actually mandate advanced dynamic analysis? Well, according to standards like IS 1893, traditional equivalent static methods are really only permissible for regular low-rise buildings. The second a structure has non-parallel lateral systems, soft story irregularities, or crosses certain height limits, you instantly trigger a mandatory response spectrum analysis to capture that frequency-dependent shaking. And for highly critical structures, say a skyscraper over 200 meters or a hospital in a highly active seismic zone 5, you escalate straight into time history analysis, which requires the step-by-step integration of actual recorded earthquake ground motions. Now, when you're calculating base shear for the design horizontal seismic coefficient, you've got to watch 2 variables like a hawk: Z, the zone factor, and R, the response reduction factor. Over in India, the latest IS 1893 update officially recognizes seismic zone V, which essentially doubles the design demand compared to zone 5. But here's the trap. Engineers sometimes default to an R factor of 5, which is meant strictly for highly ductile special moment resisting frames. If you apply that to just an ordinary non-ductile frame, you're leaving your design unconservative by roughly 40%. That is a massive risk. Next up, Section 4, Independent Third-Party Design Checks.
Look, relying entirely on the original design team to spot their own errors is a major blind spot. That's why independent proof consultancy is absolutely mandatory when triggered by 4 high-risk scenarios. We're talking innovative designs like base isolation, high public risk projects like hospitals or metro stations, extreme seismic complexity involving nonlinear analysis, and modular construction. Modular is huge right now, but it introduces totally unique temporary lifting and transportation loads that just don't exist in conventional building.
To put this into perspective, major institutional bodies have directly embedded these external audits right into their legal compliance manuals. In India, the CPWD Works Manual strictly requires independent external monitors for large projects. Urban transit systems like the Chennai Metro use project management consultancies to audit detailed designs. We're even seeing state-level mandates in places like Maharashtra, demanding mandatory structural audits to hold local bodies accountable. It's becoming the standard everywhere, as it should be. Moving into Section 5, Robustness and Progressive Collapse Mitigation. Progressive collapse isn't just an equation, it's a life-saving engineering philosophy that asks a very stark question. If one specific column is completely destroyed by an abnormal event, will the rest of the building hold up? Or will it come crashing down like a house of cards? We learned this the hard way with the tragic Ronan Point apartment collapse in 1968. A single gas explosion brought down an entire vertical tier of that building, proving once and for all that a localized failure simply cannot be allowed to doom the entire structure. Because of that, modern codes now use a multi-tiered defense strategy to guarantee structural robustness. First up is the indirect method, which uses threat-independent mechanical tie forces just to ensure continuity. Then we have specific resistance, a threat-dependent approach where we heavily harden key elements against expected impacts. And finally, the alternate path method. This is where we mathematically prove the building can bridge over a suddenly missing gap, often relying on catenary beam action as the absolute last line of defense.
And finally, Section 6, Lifecycle Durability and Waterproofing. Let's be real. Concrete cover is your absolute primary armor against corrosion, but how we calculate it varies. The Indian code, IS 456, and the American code, ACI 318, largely rely on prescriptive minimum tables based on exposure classes. The European framework, Eurocode 2, takes a different route. It uses a highly optimized, performance-based approach. It calculates a nominal cover by adding a minimum bond cover to an explicit allowance for construction deviations out on the site. It's a dynamic calculation that's perfectly suited for planning 100-year infrastructure. And we can't talk durability without talking waterproofing. It's not an afterthought, it's a fully integrated system that must be decided during the design phase. Best practice dictates the 4D strategy: deflection, drainage, drying, and durability. Your pre-construction specs have to be precise. We're talking liquid-applied systems for tricky, irregular shapes and heavy-duty sheet membranes for massive foundation slabs. Plus, there's a huge shift right now toward crystalline additives. These are amazing because they provide internal protection, chemically reacting with moisture to literally block the pores within the concrete matrix itself. All right, to quickly recap everything we've covered today, we just navigated the complete pre-construction structural lifecycle. We mastered global code variations, integrated factual geotechnical reporting, and identified those critical triggers for advanced dynamic seismic analysis. We also looked at the necessity of mandating third-party proof checks, engineering alternate load paths for robustness, and planning for genuine 100-year lifecycle durability. For your reference, here is the exact list of technical standards and codes we cited throughout this explainer. I highly encourage all of you practitioners to dive deep into these specific codes, whether it's the Eurocode 7 Geotechnical Frameworks or the U.S. Department of Defense Robustness Guidelines, to continue your professional exploration. I'll leave you with this final thought today. Robustness is an inherent property of the structural frame, not a costly retrofit. Remember, true engineering excellence begins on paper, long before a single drop of concrete is poured. So, how will you integrate this proactive, multi-codal resilience into your next pre-construction design phase? Thank you for joining me today on Bodhi Unified Flow. I'm Dr. Mari Muthu, and until next time, keep simplifying complexity and amplifying your performance.